Shall we start? Empezamos. So, good morning and welcome to a new seminar of the Blas Cabrera Institute. It's my pleasure to introduce you Manuel Izzquierdo from the European XFEL facilities. So Manuel, after graduating in fundamental physics at the University of Cantabria, started his professional career at the University of Twente in the Netherlands. In 1996, working on applications of high-temperature superconducting squids to the heart magnetometry of human fetuses. In 1999, he joined the Franco-Spanish beamline at Lure Synchrotron in Orsay, France, specializing in soft X-ray techniques for the study of materials. His scientific activity in the field of superconducting cuprates and superconducting cuprates and the master's degree at the University Autonomous of Madrid, theoretical methods in condensed matter physics, awarded him a European PhD in 2003, titled Electronic Structure and Charge Order in Superconductors of very complicated formula. In 2004, he joined the tempo line of the Soleil synchrotron, designed to perform femtosecond time-resolved experiments using the femtoslicing technique. In 2011, he did a one-year sabbatical at XFEL, which extended into a guest scientist position through a research project in collaboration with the group of Professor Liechtenstein at the University of Hamburg. In 2013, he became staff scientist of the SCS instrument at XFEL. And in 2018, he was appointed head of the photoelectron spectroscopy laboratory at the SEC group. Since December 2020, he has been responsible for the SXP experiment at XFEL. So, welcome, Manuel. Thanks for coming, and the floor is yours.
Yeah, good morning, everyone. Thank you for having me here. So, it's a great pleasure. I'm going to start some timer, so if you hear a noises that I'm late, hopefully you will hear nothing. So I'm going to talk to you about what has been keeping me busy professionally, and so basically understanding femtosecond dynamics in nanomaterials, and my goal or my dream is to do this in a single experiment. So for this, I use light matter interaction, and there has been in the past century two great achievements. One was the discovery of synchrotron radiation at General Electric in 1946, and the second was the first realization of the laser in 1960 by Hyman in this Nature paper that ended up in Nature because after two unsuccessful trials at PRL, he was forced to send it to Nature. So these two technologies have been evolving over the years in a parallel fashion and also in a complementary way. So on the one hand, X-ray sources, accelerator X-ray sources, have been excellent in increasing the brilliance very much, and also in reaching very high photon energy, so up to 200 kilo electron volts, with some limitation regarding the time structure that is inherent to the fact that you have the electrons in a circular orbit, and you have to match Betatron oscillations, and this results in a particular width of the electron bunch, and as a consequence in a particular width of your photon pulses. This changed in 2000 with the implementation of femtoslicing technique that I will present you in the following, and later with the development of free electron lasers that I will also briefly discuss. Parallel to this, the laser community, they have been extremely successful in reducing the time duration of the pulses, and they reach sub-picosecond already in the mid-70s, and now we are at a second. So in the year 2023, there was a Nobel Prize awarded to harmonic generation and attosecond pulses. however, the challenge comes on the other side, so increasing the photon energy to understand, to study materials. So I want to go back. So basically, it took them up to the 2005 or so to go above 100 electron volts, and so we are now reaching here around 700 electron volts, and there are some propositions that say that we should be able to go even higher in photon energy. So both accelerator-based and lasers have been used to study the dynamics of materials. In the case of synchrotron radiation, the limitation of the pulses has also limited the possible studies. So some of the early experiments were done studying surface photovoltaic effect in this silicon oxide on silicon 110. And as you can see here, they only managed to do the experiment with nanosecond resolution. Over the years, the technique improved, and one of the fields where synchrotrons have been very successful is in the study of magnetization dynamics, because there are many relevant time scales that match the pulse duration of the pulses that one can produce on a synchrotron. On the contrary, lasers, they managed to go earlier into the femtosecond regime, and here is one of the first studies that I had read on. This was a study on polycrystalline gold, and basically they excited the material with a laser, 800 nanometers, and then they probed the response as a function of time delay, and you see here that you have already a sub-picosecond resolution, and then basically what they did is studies as a function of the fluence at different times, and then they modeled this with this kind of model where they assume that basically these two temperature model, they assume basically that the laser excites the sample, and then you have two baths. One is the electronic bath that gets very hot upon laser excitation, and then there is an exchange with the lattice. This information is results from modeling. You can write some rate equations. However, you cannot really understand how electrons modify and how they transfer to the lattice and how the lattice changes. So, in this respect, so if you want to do this and to go, you want to understand, you need to have, from the laser side, you need to have higher photon energies, and this has been achieved in two different ways. On the one hand, you have plasma betatron sources that produce X-rays in what we call the X-ray regime, so 10 kilo electron volts or so. And on the other hand, up to a few hundred electron volts with using the harmonic generation that you see here, this paper from Alullier, who got the Nobel Prize last year. And then, so basically, this technique is what has allowed to go above 1 kilovolt. Accelerators, on the other hand, they did something similar. They went into the femtosecond regime by using a technique that is called femtoslicing. And basically, the femtoslicing technique is based on the fact that if you have an electron propagating in an undulator, and you make an interaction with a very powerful optical laser, basically what you are going to do is to introduce a modulation of the electronic density, and what is going to happen is that you will create these wings in your electron bunch with a duration of femtosecond, and the radiation that they will produce will be in the femtosecond regime. This was demonstrated in 2000, and it has been used since. The caveat of this is that it's a very low efficient process, because basically the efficiency depends on three factors. One is the relative time duration between the laser and the electron band, so basically it's in the order of 50 femtosecond for the laser and 30 picosecond for the electron bands. The repetition rate between the two, so normally lasers, these powerful lasers, they run at up to 10 kilohertz, and then the synchrotrons normally run at 500 megahertz. And then there is a third factor that is linked to the interaction of the laser with the electron, the efficiency of the interaction of the electrons with the laser. So this results in an efficiency of 10 to the minus 8. So basically you end up having 10 photons per second that are usable for experiments. And the advantage of femtoslicing is that you can produce both soft and hard X-rays. So both have been used up to date. So you see here one of the latest experiments published at the Femto Express station at BESI, where basically they use femtoslicing to study ultrafast induced magnetoptical changes in using resonant reflectivity in this kind of compound. The high harmonic generation sources have been used also to study, for instance, this compound that has application for light harvesting. What happens is that, well, you can get some dynamics, but you need a very detailed model in order to understand what is going on in this data. So there is the ultimate realization of femtosecond time-resolved experiments has been made possible thanks to the development of X-ray free electron lasers. The proposal was done in 1982 by Kondrachenko, Saldin, and Derbenev. And basically, the idea is, due to the fact that there are no mirrors that can be used to bound a seed between, and there is no media, so they propose to use an undulator as a gain medium. And basically, in order to avoid the use of mirrors, basically what they said, okay, let's make the undulator as long as it's required. So what happens is that at the beginning, you are going to have your electrons in this fashion. So basically, this is the typical electron packet that propagates in a synchrotron. But as it propagates through these hundreds of meters of undulators, what is going to happen is that due to the interaction of the electrons with the electromagnetic field that they produce, a microbunching effect is going to happen. And this will lead to slices of electrons lacing coherently. And as a consequence, the power of the radiation will be proportional to the number of the electrons to the square, and this is what makes the sources so brilliant. And the coherence comes from this microbunching directly. So, you can produce again up to 30 kilovolts, even higher. I'm going to concentrate on what you can do with soft X-rays, basically between 0.3 and 3 kilovolts, and which is my area of expertise. And I see some advantages. Probably I'm totally biased. So one is that you cover essential resonances. So for instance, if you look at the periodic table, you see that the K shell you can measure up to sulfur. The L shell you can measure up to niobium, and the M shell you can measure up to lead. And this covers very relevant materials for planet Earth, like for instance carbon, nitrogen, and oxygen, and also the 3D materials that have very many potential applications. A second advantage is that the wavelength is in the order of 0.4 to 4 nanometers, so basically it's ideal to study nanomaterials. And then the cross-section is also optimal because the photoelectric effect is going to dominate up to around 12 kiloelectron volts, and from there on other effects come into play. So, but this means that the light-matter interaction process is going to be very efficient. What is the challenge? The challenge is that With this wavelength, and the fact that there is a very strong photoelectric absorption, you are going to have challenges in sample preparation, because normally your samples have to be thin, or you have to see how you to best do your experiment. So I'm going to present one example from my own research, and this is the case of lanthanum cobalt oxide. So this is a 3D perovskite, and this compound has been investigated for more than 50 years based on the fact that there is a low temperature spin transition around 100 Kelvin, and then the system also has like a semiconductor to metal transition that goes very smoothly from room temperature up to around 600 Kelvin. So the debate is what is the excited state of the system. So at low temperature, everybody agrees that the system is in a low spin configuration. Basically, you have all the T2G orbitals full and the G are completely empty, and then you have this configuration, and then the ionic radius of the cobalt 3+ in this low spin configuration is 0.545 angstroms. And then there was a first model proposed by Goodenough and Rakak. So basically they said that the transition has to be from low spin to high spin. So basically a spin 2, T2G is with 4 orbitals, 4 electrons, and then 2 electrons go into the EGs, and then this results in a much larger ionic radius. However, in the 90s, LDA calculations using correlations with a U factor of 7 proposed a different model, basically proposed a possible transition to an intermediate spin state, S1. Basically what happens is that you have 5 electrons in the T2G orbitals and 1 electron in the G orbitals, and the ionic radius is kind of in between. This material, maybe because of the fact that the theoreticians were discussing it very, very heavily, trying to understand what was going on with this spin transition, was studied in other many aspects, and it was shown that it has excellent properties, for instance, in CO and NO trapping, for instance. It can be used for thermoelectric power generation, for gas sensors, catalytic oxidation of hydrocarbons, and even for oxygen permutation membrane. So it's a relevant material. You can also use it to purify water. So we wanted to understand this, and then the first problem we faced is that, so you say, okay, I want to study with SOFIC rays, so what I can do is I make a thin film, and then I understand the material using conventional techniques. However, this material, when you grow it in a thin film, well, what happens is that the paramagnetic to the diamagnetic to paramagnetic transition disappears. At low temperature becomes ferromagnetic, and there is also some ordering of the lattice due to a strain of the substrate. There is also basically the lattice changes. You don't have this structure any longer. You have like an orthorhombic. So basically there was no way of doing this in the thin film. So basically we were left with 3 options. One is to study bulk reflectivity. Another is to do microcrystals using microtomy, and the third would be to prepare lamellas with FIP. I'm going to discuss the first 2 cases. So the technique of use was, or what we thought was possible, was to use X-ray absorption spectroscopy, and then you can do studies both at the cobalt LH and at the oxygen LH. And so the cobalt LH gives you information, the electronic and spin configuration, and the oxygen KH give you much more information, because basically if you have a perovskite ABO3, so basically the first part of your oxygen absorption spectrum gives you information of the hybridization with the B atom, in this case would be cobalt. The medium part with the A atom, in this case lanthanum, and the last part gives you information of the hybridization with the cobalt sp band that is linked to structural changes. So, and if you study the system as a function of the temperature, you see that what's going to happen is that you start with fully populated T2G, so this is empty, and as they depopulate, you see here a shoulder that increases. So we did a first experiment with femtoslicing using 800 nanometer pump, and so when you go to femtoslicing, you have to give up on something because you know that you have very many, not that many photons, and we gave up on energy resolution. So basically, you see the blue gray spectra. This is what happens when you measure with your sample with a plain grating, and then the black is when you measure with femtoslicing. The advantage in the second case is that you have a femtosecond resolution. The summary of experiments is as follows. So basically, we measure. So if I go back. So basically, what we did is we measure at resonant energies relevant to the T2G orbitals, to the EG orbitals, and to the cobalt 4sp band. This for oxygen, and then in the region of the shoulder of the white line at the L3, where the high spin state of the system is supposed to show up. And then the summary would be as follows. So basically, this is what happens as the T2Gs, as they become depopulated. You have an increase in the absorption. The EGs the opposite, and then at the cobalt LH, you see this kind of shape. And at the oxygen cobalt 4sp, you see this decay that is very slow. What we also found was something very interesting, is that if you just take combinations of these two delay scans, if you make the sum, so you end up with this delay scan that is very similar to what happens at the cobalt 4sp band. And if you make the difference, you end up with this green one that is very similar to what happens at the cobalt LH. And so our understanding is that basically by understanding what happens to the T2G and EG orbitals, you should be able to disentangle what is going on with your system. So based on this, we proposed a model where there is first carrier excitation, then there is a charge transfer enhancement due to the orbital redistribution and the fact that the EG orbitals become populated and they look along the two in this direction, cobalt, oxygen, cobalt. Then around 1 picosecond, there is a spin stabilization, and at last, the lattice also follows with much slower. And the conclusion is that the oxygen KH encloses all dynamics. So then X-FELS became available in the meantime, and in particular SASE-3 with this availability of between 300 electron volts and 3 kilovolts. And then we decided to investigate it again. So, but the problem of free electron lasers is that they have all pulses are different in intensity and impulse energy, and for this, so we implemented a method at the SCS, which is the beam split of axis sum plate method. So basically what you do is you make your sample in membranes, and you use this element that is the grating and a focusing element, and then this passes through these three membranes, and then you measure 3 images in a fast detector DSSC, and in principle one should be empty to have an I0 reference, the other one should be with no laser to have the static or unpumped, and the others should be with laser to have the pump. And from there, by doing combinations, you are able to calculate the different spectra with a signal-to-noise ratio that approaches very much the shot limit. You can see here the shot limit results and what we can achieve. So when you do this, so basically you see that there is an advantage of free electron lasers. First of all, we are able to measure energy scans at pump probe energy scans at selected times, and then you see here this spectrum. You can do this at very many times, as many as you want. I'm only going to present you this example, and then again you can focus on what is going on. This is the T2G orbitals, this is the EGs, this is the lanthanum region, 5D region, and this is the cobalt for SP band. So in this case, we wanted to give a twist, and then we decided to, instead of using 800 nanometers, we wanted to do a sub-gap excitation of the system. And so when we analyze the data, so what happens is, because we have high pulse energy and high repetition rate, so basically what happens is that now your delay scans are much richer in structure, and you are able to see the same components that we saw before, but we also see some oscillations in the residual. That is related to the fact that we are exciting some low energy modes. So basically you can do an analysis of this by doing Fourier transformation, and then we have found that the main excitation, depending on the resonant energy you're looking at, can go between 1.33 terahertz and 1.99. This data is still under analysis to understand, because in principle what we know is that this 199 terahertz is assigned to can be assigned to a phonon mode, but the other, in principle, there are no phonon modes that can be responsible of these oscillations. So the conclusion is that Sophic rays allow understanding multiple time scale dynamics and also the entanglement between the different degrees of freedom of the system. The problem is that for the lattice, only the dynamics is available. So if you want to go further, are there other possibilities? Well, one very appealing possibility is to do a femtosecond time resolved photoelectron spectroscopy, because in principle you can access the valence band electrons and understand the electronic properties and also the spin properties if your spectrometer is spin resolved. You can look into core electrons, and then you can analyze the chemistry of the system, but you can also understand electron-electron correlations and many other effects in your material. And you could also do time-resolved photoelectron diffraction, and from there you should be able to understand how the lattice changes at the same time as the electrons, the chemistry, the spin changes. Note that this example is not from photoelectron diffraction in forward scattering, that has not been yet realized. So this comes from ultrafast electron diffraction, but one would expect something like this. So this is an example on this material. So this dream has been not possible for many years with femtosecond resolution. And the reason is that so far there was no source available. So why is that? Because if you use very high fluence pulses and you have not that many pulses, this is typically a warm free electron laser running at 120 hertz or 200 hertz. So basically you induce space charge effects. And you can see this in this example that was even measured in a synchrotron, so you don't even need to go to a free electron laser. So if you have on your sample something in the order of 10 to the 2 photons per micron square, you will be able to measure the band structure and the Fermi surface of your material. As you start increasing there, due to this nonlinear effect, what's going to happen is that you will have distortion on the spectra, and then at this limit of 10 to the 4 photons per micron square, which corresponds to 150 I0. So basically what happens is that the shape of your valence band is completely distorted, and the Fermi surface is distorted. So you can correct this, of course, but when you do a pan-probe experiment, so you want to make sure that you start with a well-defined ground state, because it might be that this could be also induced by your pump. And so in order to do this, what you need is to have a source with moderate flux, but with as many pulses as possible. And in the Sophic ray, so the only possibility of realizing this today is by using superconducting free electron lasers that allows to produce pulses with megahertz repetition rate. What possibilities are there? So the first one that was available is flash, but it barely reaches the Sophic rays, because basically in first harmonic you can go up to 300 electron volts. if you use thermonic, you can reach up to 700, 800 electron volts, so close to 1 kilovolt, but not yet. And then, since last year, we have the SXP instrument in SASE-3 that covers the Sophic ray range between 0.3 and 3 kilovolts, and LCLS2 is in commissioning phase, and they are supposed to be able to provide this type of experiments between 0.3 and 1.5 kilovolts. In 24, maybe the commissioning and the first experiment in the year 25. And then there is also a project in China, SHINE, that are supposed to start doing experiments also next year. So some of the things that this possibility has enabled, so I am going to go very briefly here. So for instance, it has been used to study excitonic mode transition in tantalum diselenide by doing a resonant excitation at 1.6 electron volts of the exciton and see how the system evolves as a function of time. So it has been also used to study phase transition. This is a very classic example of the antiferro to ferromagnetic transition in iron rhodium. This was done already above 100 electron volts, so overcoming what is available with high harmonic generation sources. It has been used to do the first photoelectron diffraction experiment, so on bismuth diselenide. So, and also to study charge transfer in light harvesting materials. I'm going to focus in the next in two examples. One is the study of the ultrafast electronic bandwidth in graphene, and this follows a proposal from the 60s that wanted to, from the 60s, so that basically they proposed what would happen to a core level when you do a very high excitation, and how high could the electronic temperature of the system go by keeping the material still intact. So these colleagues, they did an experiment. They excited graphene with 155 electron volts, so basically around 800 nanometers, and this fluence 0.5 millijoule per square centimeter. So, and then they probed the material with 337 electron volts. So, and basically, so this is the core level, the carbon 1s core level as a function of time, and this is the different scan. And what you can see is that, so basically you see a huge increase in line width of the core level, and basically what they did is they analyzed the profile of the core level by using by starting with this with expression of the XPS intensity proposed by Hughes and Scarfe in 1996, where this part takes into account some electron hole interactions and things like this. So basically they realized that they had to modify this because the system in principle was so hot that you cannot just consider that you only have interactions from below the Fermi energy to above, so you can also have a recombination and recoil and all these things from excited electrons. So, and basically what they managed to do is they managed to fit this. The blue is the fitting, and so, and then the green represents the electronic temperature. So then they plot this as a function of time, and they were able to see how the electronic temperature evolves with time, and they saw that at the very short time delays, the electrons in the system can be as high as 5,000 Kelvin. They did a simultaneous experiment of photoelectron diffraction, and they saw that in spite of the fact that of the high electronic temperatures, the system is still, there is still a lattice, so the lattice of the system still remains, and with not very big changes. The second example I'm going to present is example on photocatalysis, and in particular water splitting on titania. So this is kind of like a seminal example. So basically, it's known that photocatalysis of water occurs only on the unattached phase of titania due to the bond distances at the surface. And what the colleague did, so basically they did again a probe experiment because it's a photocatalytic process. So they again excited with something around 800 nanometers, and they probed with 645 electron volts because they wanted to see the dynamics at the oxygen 1s. So they did the first experiment where basically they measured the pristine titania, and the pristine titania prepared under very special conditions. So basically they did the annealing in oxygen atmosphere to make sure that there were no vacancies or interstitials into the system, so to get the surface as stoichiometric as possible. And then when you do a time resolved experiment, and then you take a spectrum in this area, this is red, and this other area, this would be blue. So what you see is that there is only around time zero this excitation that is what we call sidebands, and this is related to the interaction of the laser with the electrons getting away from the sample. However, you can see that there is no change in the position of the peak. So basically, there is no surface photovoltage effect, and this is a proof that your surface is as stoichiometric as it could be. On the contrary, if you now absorb water, basically less than one monolayer, around 80% of the surface was covered. You see here a faint line showing up that is related to chemisorb and physisorb water. And then in this case, when you shine with the lasers, then you see that there is a change of the binding energy of the material, and this obviously, if this is not related to surface photovoltage, this is related to the fact that the hydroxides on the sample, there is going to be a charged Hall transfer from titania to water that results in this chemical shift. Because they had a coverage below one monolayer, so basically you can see here that the water feature is very weak. So and they also saw that by integrating regions of around 1.2 picosecond, so very quickly after the excitation, the system became kind of stable. So what they did was they add up the spectrum before time zero and after time zero. And so what you can see here, when you multiply the water part by a factor of 5, so basically what you see is that there is a broadening of the peak and also a movement toward lower binding energies. And so basically this implies that there is a second component that is formed. So then the group of Angel Rubio, they did some Ehrenfeld simulations to understand what's going on with the system. And let's see if this works. So basically, you start with this system where water is on a titanium 5C site, and then you see what the interaction is going to do as a function of time. So basically, what is going to happen is that there will be a bond that is formed between the hydrogen and one of the oxygen 2C sites, and this reduces the distance from the 3.2 that we saw at the beginning to 1.72, and this allows explaining what is happening in the system. You see here snapshots at different times. So here you have 0 femtosecond, then after 100 femtosecond, you see that the bond length due to this extra stub bond is changing, and then this is the final configuration of the system. as you saw, this experiment was only at 650 electron volts around. So yes, for this we have built the SXP instrument at the European IQF-CSIC. So basically it's a typical free electron laser instrument, a little bit more compact. So basically, so we have the usual elements. So we have a laser alignment system. We have a focusing for X-rays with it's a KB system in this case. We have a pulse arrival monitor to measure the relative arrival between the optical laser and the FEL. We have a laser coupling system to couple the optical laser into the system, and here we have the experimental station that is equipped with a momentum microscope in the vertical configuration. So what is important to know is that we are using the so-called momentum microscope, and momentum microscopes are very complicated machines, but they are also very powerful because you can do both beam experiments, but you can also do experiment with angular resolution. You can even put a spin branch to do also spin resolve experiments. So basically, the device that we have has a large angular cone around 40 degrees. We have a MCP-DLD detector to do pulse resolve measurements, an energy resolution around 130 millielectron volts. It's a spin integrated, and you can mount a standard Omicron samples. In order to do pan-probe experiments, what we have is the PP laser provided by the European IQF-CSIC. So basically, it can run between 100 kilohertz and 4.5 megahertz. It has two outputs, one at 800 nanometers and the other at 1030. And then you can also do second and third harmonic. And then there is the possibility of extending the wavelength range by using an optical parametric amplifier. Right now it's running at 118 kilohertz, at least in SACE3. And now we are making efforts to make it running at 562 kilohertz, and from there you can go from 200 nanometers to roughly 15 microns. So basically you could use all these zone to excite phonons directly and see how your material reacts to the excitation on phonons. There is also a new add-on that is coming, which is the production of terahertz to use them as a pump. So here is a summary of the commissioning. So we did last year. So basically, we have this is a ping image here. We measure with a mercury lamp, both HSI, and you have here 100 times 100 micron with 10 micron squares, and from there, and this is the FEL as imaged by the mercury lamp, and you see that it's in the order of 10 rough times 90 microns, which is what we were expecting from the KB system that we have. In PIN, we have an ultimate, we can resolve 1 micron structure, so the typical resolution in PIN mode is around 500 nanometer, which is worse than dedicated PIN system, but still allow us to do experiment with submicron resolution. And then the femtosecond dynamics. So basically what we do is to measure what we call laser assisted photoemission, so LAPE. And basically you see here the LAPE experiment we did on goal 110. That is going to be one of our references. And then you see here, these are the two core levels, and then you see these the orders of LAPE that you can excite that depend on how clean your surface is and how powerful the experiment, the laser is as well. So in April this year, we did the first experiment. So basically we did femtosecond XPS on tantalum disulfide. And this system is very interesting because it has a very interesting phase diagram as a function of the temperature. So basically at low temperature you have a commensurate charge density wave. Around 200 Kelvin this changes. And then at room temperature there is a non-commensurate charge density wave that's above 350 evolves in an incommensurate charge density wave. It's very interesting that you can follow this evolution by measuring the tantalum 4F core levels, because basically this is going to induce the charge density wave is going to induce splitting. that depends on the temperature, and you can also analyze as a function of PAM probe. So basically, so this is what was measured in 2010 at flash. So basically, you see here the two peaks that appear when you are at low temperature in the charge density wave phase. So what we did was to mimic this by cooling the sample to 150, which is the minimum temperature we can reach now. And then the difference between these two is that this experiment was done at 100 electron volts, and here we did the experiment at 1 kilovolt. And then, so we first, before cooling, we pumped the non-commensurate charge density wave state, and basically you can see here that you also induce LAPE on your sample. And then something that you can hardly see is that when you pump the charge density wave, there should be some dynamics, and time zero should be around 310, but it's not very clear. Let's hope the data analysis will show better results. And with this, I want to acknowledge all my colleagues at European XFEL. As you can imagine, building an instrument is a collaborative effort, so we are 500 people, so all contributions are important. I also want to acknowledge the time-resolved photoelectron spectroscopy community that have been very helpful during the commissioning of the SXP, and also the SXP group. You see here a picture of all of us. And then I also want to thank you for your attention.
Okay, thank you, Manuel, for this great talk. Now it's there's time for questions from the audience. Some questions from people in the area of lasers and materials. It's quite far for me. Nobody wants to join the discussion.
So the spatial resolution is 1 micron.
You can resolve 1 micron structure. The resolution is 450, 500 nanometers. So it's worse than a PIM. And this is because you have to make compromises in order to be able to also obtain the angular resolve, the momentum resolve image.
Okay.
Yeah.
And how do you use it with the spin analyzer?
So for the moment we don't have, but basically, well, you use basically the standard. So you can put this ferron material, and then basically you do a scattering, and then you measure the spin polarization on the other detector, if you had one.
So you measure with one spin, with the configuration, and then with the other, and then you combine the results.
Yes,
okay.
classical, yes.
Okay.
Anybody else? All right, so I think that we can thank Manuel for this contribution and explanation here today. And also, we would like to give you this as a
Thank you so much.
as appreciation for your visit. Thank you.